Hello friends, welcome to Susan and John MathTube. This is the first lesson in 3D geometry. And in this lesson, we are going to learn the basic concepts of 3D. Okay, so before we start the three-dimensional geometry, I wanted to show the three-dimensional plane. So you can see that it's made up of three axes. The red axis is the x-axis, the green one is the y-axis, and the blue one which controls the height and depth. The blue one which controls the height and depth is the z-axis. Okay, I want you to notice these things. You will understand that the three-dimensional system is divided into 8 equal parts. In 2 dimension, everything is divided into 4 parts, right? Because when we draw the x-axis and y-axis, the whole plane will be divided into 4 parts. And similarly, in the 3 dimension, we divide the whole system into 8 parts. And each part will be called octant. And you know that octa is related to 8. So each part is called an octant. And like in the two-dimensional geometry, if you look at this, you can see that red is x, green is y, blue is z. Okay, you can see that this is the first octant. I am calling it the first octant because you can see that all the red numbers are positive, the green numbers are positive, the blue numbers are positive. That means in the first octant, all will be positive. X will be positive, Y will be positive, Z will be positive. Then what we do is, we move to the second octant, third octant, fourth octant, and you can see the remaining things below. Okay, now I think you can see a few planes. One is our usual plane, the plane which you used to learn. Look. Our x-axis and y-axis. Can you see? This is our 2 dimension. See? X-axis and y-axis. So this is called xy plane. And you remember, in the xy plane, the z coordinate will be absent. And these planes are yz plane and zx plane. The second thing I am going to tell you is, in 2 dimension, just like I told you, there are 4 quadrants. And in 2 dimension, if you consider a line, we always ask for a concept called slope, or we always search for a measurement called slope, which you learn from class 8 or class 9 or from your basic mathematical level. So remember, in 2 dimension, we have developed a concept called slope, which is associated with line. That is, we measure the angle and then we take the tan, and then in higher classes you learn so many methods to evaluate the slope, like the derivative, etc., and you found so many applications of slope. But remember, in 3-dimensional geometry, when we have a line, never ask for slope, because we have not defined slope in 3 dimension. So I want you to make this part very clear now itself. In 2 dimension or in 2-dimensional analytical geometry, we associate every line with a measurement called slope. But in 3 dimension or 3-dimensional analytical geometry, we do not have slope of line. So that is exactly where we are going to start. Okay. Now, no need to worry. Instead of slope, we have an alternative concept called direction ratios. What do you call that? Yeah, direction ratios. Okay. If you want to understand direction ratios, first of all, you have to consider let's say a line in 2 dimension. And now I'm going to take 2 points on the line. The first coordinate is x1, y1, and the second coordinate is x2, y2. Now I want you to look at the line segment AB. First what I do is I'm going to project this line segment on the x-axis. I'm going to project this line segment on the x-axis. By the way, projection means shadow of the line segment. You can imagine we are putting a big torch over here. And we are finding the length of the shadow. What are we finding? Yeah, the length of the shadow. This much length is x1. Because the coordinate, think about it. If you have a coordinate 2, 3, that means you're going to move 2 units along the x direction and 3 units along the y direction. So the coordinate is x1, y1. So that means this much of length will be x1. And from the origin to this point, so this much length will be x2. Or in other words, the length of the projection, or simply mathematically the projection, will be x2 minus x1. So once more I'll tell you, we are planning to study a very important concept called direction ratios in 3 dimensions. But if you want to understand the concept, first of all, you should understand this. That is, you consider a line. And remember, line will be infinite in length. No one knows the beginning, no one knows the end. Now what I did is I took 2 points on the line. And the projection on the x-axis turned out to be x2 minus x1. Now similarly, I'm going to make this y-axis a little bit bigger. Yeah. Similarly, now I am interested what might be the projection in the y direction. See, I'm going to project it in the y direction. That means I'll get this much length. Obviously, that will be y2 minus y1 because this much of height is y2 and the small height is y1. Okay, I will show you one more small thing which will be very useful for you. Look at this. We just proved that this length, that is the projection, is x2 minus x1 on the x-axis. And you just proved that this height, look, parallel to this, is y2 minus y1. Now if you apply Pythagoras theorem, we will understand that A to B distance will be root under x2 minus x1 the whole square plus y2 minus y1 the whole square. Wait a minute. I've seen this before. Okay, this is our distance formula. But now I am going to give a different interpretation for the distance formula. Distance between 2 points in a line, is square root of the sum of the projection squares. Isn't it? Look, distance formula is nothing but sum of the squares of the projections under a square root. Okay. Now, with this enlightenment, once more, let's make it very clear. You consider a line segment, take any 2 points on the line. The projection will be nothing but x2 minus x1 in the x direction, and that will be y2 minus y1 in the y direction, and probably in the z direction it will be z2 minus z1. Okay, I'll show you one experiment. Look at this. I took 1 point on the space. You can read the coordinate here, 1, 3, 4. So look at this. I have a point 1, 3, 4 on the space, and another point 3, 5, 6, and then I have a line. Actually, we can think like this. I took 2 points on the space. I have a line and I took 2 points. So look at this. It is analogous to the concept I was telling you in 2 dimensions just now, so that you will understand very easily. I took 2 points on a line. namely A and B. Okay, now I'll show you how the projection works in 3 dimension. I hope now you can see the projections. I'll magnify it a little bit. I hope you're able to see the projection. See, I took 2 points on the line, and can you see the projection along the x-axis, the red color one, the projection parallel to the y-axis, and of course the difference in height. See? Okay, I'll show you these concepts more clearly. I'll do one thing. I'll take 2 other points. So I took 2 other points E and F. I think you can see the points E here and F over here. And now I'll show you the projections. See? So you have to understand, corresponding to any 2 points on the line, there will be a projection parallel to the x-axis, there will be a projection parallel to the y-axis. You can imagine like you're moving from here to here. I hope you're able to see the projections clearly. Okay, now look at this. And by the way, when I say projection, I mean the length of the red segment, length of the green segment, length of the blue segment. So I think the graphics are enough for you. Okay, now let's go to the topic. So what I am trying to convince you here is a very simple concept. In 3 dimension, if you have a line and if you take any 2 points on the line, you will be able to see projections parallel to the x-axis, projections parallel to the y-axis, and of course projection parallel to the z-axis. And the length of the projections are denoted by A, B, C. And these quantities are called the direction ratios of the line. Now earlier I showed you, like first I took 2 points A and B, and you saw the projections are like a little bit, that small red segment, the small green segment, and the small blue segment. Later I took 2 other points very randomly. It's like 4.28. Look at the coordinate. It's so random. So later I took 2 other points, E and F. And then I showed you the projections are big red line, the big green line, and the big blue line. Now there is a question. Do you think there is some sort of connection between them? For example, if I take other 2 points, I can take 2 points here. Someone else may take 1 point here and another point here. So every time I'll get some sort of values for A, B, C. I'll get A1, B1, C1. Another time I'll get A2, B2, C2. Another time I'll get A3, B3, C3. But remember, we have an amazing property. All these values will be multiples of each other. Or more mathematical, I'll put it like this. They are proportional quantities. Okay, I'm sure some of you are still confused. So look at this. We are in 3-dimensional system. In the 3-dimensional system, we have our x-axis, the y-axis, and the height controlling device or the axis will be the z-axis. Now imagine we have a line in 3 dimension. It's very hard to plot here. That is why I'm using the software. So you can imagine a line floating like this. Now my aim is very simple. I want to develop a concept called direction ratios which will compensate the concept of slope in 2 dimension. I want a replacement of the concept called slope in 2 dimension, and that is called direction ratios. And the concept is defined in a very simple manner. Take any 2 points, anywhere. The line is infinite in length. You can take 2 points here, A and B. Or you can take 2 points here and here. Anywhere you like, you take 2 points. and find the projections, or if you want to be more exact, the length of the projections along the x-axis, along the y-axis, and along the z-axis. If you want to understand more, you can see it very clearly here. See, corresponding to any 2 points, you can see something parallel to x-axis, parallel to y-axis, parallel to z-axis. And those measurements are called the direction ratios, and they are denoted by A, B, C. Now, another question, because many students ask this question immediately. What will happen if I take 2 other points, namely C and D? Okay, I agree. You will get different answers, A1, B1, C1. But remember, they will be connected. The first answer and the second answer will be multiples of each other. So remember, the first answer and the second answer will be proportional. I'll show you one more thing. If you consider a line parallel to this, wow, not the same line, I'm talking about a line parallel to this. Now you take any 2 points, Okay, let's say E and F. This time I'm sure I'll get something different. Okay, I'm going to call it A2, B2, C2. Wait a minute. That will also be a multiple of these 2 quantities. So this is really amazing. You can try it out. You can use softwares or you can use models, whatever you like. You try this, you'll be amazed. Anyway, I'll show you the values here so that you'll be more convinced. Look, I have measured the length of the segments. You can see that the bigger segments are of length 6.32, 6.32, 6.32, and the measurement is very easy. X2 minus x1, y2 minus y1, z2 minus z1. That will be the length. I'll repeat, the length will be x2 minus x1, y2 minus y1, z2 minus z1. And now take a look at the smaller segment length, 2, 2, 2. So look at this. The first answer was 2, 2, 2, and the second answer was 6.32, 6.32, 6.32. Remember, it need not be the same number, but here it came the same number. But are you able to see they are proportional? This is actually 2 times 111, and this is actually 6.32 times 111. Anyway, they are multiples of 111. And by the way, you have to remember one more thing. This segment AB is a vector. And the concept called direction ratios are nothing but the components of I, J and K. EF is another vector, and the red color, the green color and the blue color are the components of the vector. And I want to tell you one more thing that I showed you here. What happened when you squared the projections and add them and put under square root? You will get the length of the line segment. So remember, if you square direction ratios and add them up, it will give you the modulus or the length of the line. Okay, so one more last time I'll try to make it clear. Consider a line. You consider any 2 points on the line. Then the projection along the x-axis, y-axis, z-axis denoted by A, B, C is called the direction ratios of the line. Now point number 1, suppose you take the points anywhere else. And I'm sure you will get some different looking answer, A1, B1, C1. But remember, this quantity and this quantity will be proportional. Okay, now suppose you have a parallel line and you take 2 points on the parallel line and measure the direction ratios. But still our answers will be proportional. So this is the concept of direction ratios. Now another thing I want you to understand is if you find root under a square plus b square plus c square, then you will get the length of the line segment. So this quantity is called modulus of the line segment. Modulus means length, distance related quantity. Okay, so having done that, now let's move to something even more interesting. And that concept is called direction cosines. Here what we do is, we consider a line. Now what we do is, we consider 1 unit of the line. How much length of the line? Yeah, exactly, 1 unit line. We consider only this much. We consider only 1 unit of the line. Earlier I told you, you can take any line segment. Maybe a line segment of length 10 centimeter or 10 meters or 100 meters, 200 kilometers, 236 kilometers, whatever you want you can do. But when we define direction cosines, we should take 1 unit line segment. And we do the same thing. We take the projections along x-axis, y-axis, z-axis, and we are going to denote it by LMN. Yeah, you're right. You're 100% correct. This LMN will be proportional to ABC. Because basically, we are taking the projections. I know that. But still, we are denoting it by LMN for a special reason. Because, okay, I'll show the calculator. Look at this. Okay, now look at this. Even though our line is not touching the x-axis or the y-axis or the z-axis, you must remember there is an angle between the line and the x-axis. And actually that is obtained by projecting, or like what you call, you just take the line and put it on the top of the x-axis. Or you move in a parallel manner and put it on, okay, if I choose this position, I think you can see the angle between x-axis and the line. And if I choose another position, you will see the angle between y-axis and the line. And if I choose another position, you will be able to see the angle between the z-axis and the line. Anyway, suppose we find the angle the line makes with x-axis, y-axis, z-axis and name them as alpha, beta, gamma. Then cos alpha, cos beta, cos gamma will give us the same answers which is given by unit projection. So look at this. If you calculate cos alpha, cos beta, cos gamma, where alpha, beta, gamma are the angles made by this line and the x-axis, y-axis, z-axis respectively, then you are going to get the same answer, LMN. And that is why unit projection is called direction cosines. And like I told you before, if you square the projections and put it under a square root, you're going to get the length of the line. But what is the length of the line here? 1. So that is property number 1. L square plus m square plus n square is equal to 1. Now another thing. You know that the graph of cos x moves like this, right? That is, our cos x is stuck between minus 1 and plus 1. Cos x is between minus 1 and plus 1. So that means our LMN will always be between minus 1 and plus 1. Or in other words, if you project 1 unit line segment in any line, the answers, the projections will be between minus 1 and 1. So that is point number 2. So that's it. That was the main part of the video. Direction cosines and direction ratios, because many students are not able to visualize direction cosines and direction ratios. That is why I made this video. Actually, you learn the same concept in class 12, but many of you might not have visualized it. But right now, you should be very clear with the concept. Okay, so look at this. You have a line, and you consider any 2 points on the line. and corresponding to any 2 points on the line, we will be able to see the projections along x-axis, y-axis, z-axis. Denote them by A, B, C, and they are called direction ratios. Now, if you consider any 2 other points, you might get other answers like A1, B1, C1. But remember, our first answer and the second answer will be multiples, proportional. Even if you consider a line parallel to this and do the same thing, then also what will happen? Our answers will be proportional. So, and another important thing I forgot to tell you. If the coordinates are known, suppose you know the coordinate like x1, y1, z1, and this coordinate is x2, y2, z2, then the length of the projections will be x2 minus x1, y2 minus y1, and z2 minus z1. That we saw in 2 dimension. It's not a big deal. You can just check it out with the software. So remember, if you know the endpoints, if you know the line segments endpoints, then the direction ratios are given by x2 minus x1, y2 minus y1, and z2 minus z1. Another interesting thing, instead of taking any arbitrary length, if you take 1 unit length, how much? Yeah, if you take 1 unit length, you will get the projections. But the projections are denoted by different alphabets, L, M, N. And what do you call? Point number 1, like I told you before, if you square the projections and add them up, you will get the length of the line segment, by the way, which is 1 unit. So that gives me an excellent result, L square plus M square plus N square equal to 1. Now another interpretation, suppose we calculate the angles made by the line on the x-axis, y-axis, z-axis. And if you take cos of these quantities, voila, you will get the same thing, L, M, N. That means cos alpha will be L, cos beta will be M, and cos gamma will be N. And this gives me, this tells me another thing. These values will be always between -1 and 1. So that's it, my friends. So I'll be back soon with another video. So till then,